Hi there, it's Richard Marr from Mars Classes again. Today's video we're going to have a look at quite a few concepts. We're going to have a look at the concept of weight force. We're going to see how it acts on an inclined plane. We're going to have a look at the reaction force that will exist due to this weight force on the inclined plane, and then we'll have a look at some resolving of forces. So if you're ready, we'll make a start. Okay, so imagine you drop a mass, say a 5 kilogram mass. Now when you drop it, it falls, and it falls because of a gravitational force pulling it down. Now that gravitational force can be, as Newton explained, between two masses just attracting each other, the Earth and the 5 kilogram mass, or as Einstein described it, as a curvature in space-time. Now imagine if we lifted this 5 kilogram mass such that it was suspended at one point in the air. Now if there was just the downward weight force acting on it, it would fall back down. So to be suspended, there must be an equivalent upward force acting on it. So if it's 49 newtons down, you'd have to have a 49 newton force upwards. Now what could provide that force? Well, we could put a spring balance on there. Not only would it provide the force, but it'll give us a mechanism of measuring what that force was. And when we do that, and we're weighing an object is what we say, we're actually measuring the size of the upward force which is balancing the weight force down. If we replace that single spring balance with two spring balances, you'll notice that each one will be now providing half of the force if they're both going directly up. So you've still got an upward force of 49 newtons opposing the downward force of 49 newtons, so the thing is in equilibrium and it's remaining where it is. Now just imagine if we move these two spring balances and still maintain the 5 kilogram block suspended in the air. Now when they move, then probably not any longer going to be providing the 24.5 newtons each. They're going to be providing some force each, which will, both of those two forces of the spring balances will balance the downward force of the weight. So this downward force of the weight is balanced by these spring balances. This one is pulling up in that orientation and this one is pulling up in that orientation. So this one here must be providing an upward component to its force, and this one here must be providing the other upward component to its force, which would balance this downward 49 newtons, but each of them will also be providing a component horizontally, and the horizontal component of each will be equal in magnitude but opposite in direction. Now we can represent those forces as vector arrows. Now when we represent them as vector arrows, we should be able to see that the red arrow and the green arrow and the purple arrow are now all going to add up to 0 because that object is just suspended in space. So let's just change the situation, not have it suspended in space but sitting on an inclined plane. There's still the same forces acting there, but now let's say we remove the spring balances and this 5 kilogram object remains stationary on the inclined plane. If it's remaining stationary on the inclined plane, all those forces would still exist and they'd still add up to 0. So when we look at those forces, we can see that they, in fact, if we add them together in a triangle, draw them head to tail, they will add up to 0, or they'll form an enclosed shape there. And with a bit of geometry, if we look at the angle of the incline, we can find that the same angle exists at the top of that little triangle there. So what's actually going on? What is the green force and what is the red force? Well, if we look at the downward purple force, which is the weight force, and if we split that into two components, the weight force will have a component which is acting down and parallel to the plane, which is represented in red on this diagram, and also have a component which is acting perpendicular to the incline. Now in physics, anything that acts perpendicularly we say is normal. Normal is just a direction. Normal means perpendicular. So if that thing is in equilibrium, the red component, which is acting down the incline, must be balanced by this red component acting up the incline, and the green component into the incline, or normal to the incline, must be balanced by this other force, which is also normal to the incline. So what could those forces be? Well, the red upward force is most likely a frictional force, and the green upward force we call the normal reaction force. Okay, again, I'll repeat, normal just means perpendicular to the incline. If you just say normal force, it is not the normal force, because a normal force is any force which is perpendicular. But what is this reaction force? If we look at the surface of the incline, it's composed of atoms. which have electron clouds around them. The surface of the mass is also composed of atoms with electrons around them. And these negative electrons on the outside of all the atoms on the incline, and the negative electrons on the outside of all the atoms on the 5 kilogram mass, they're going to repel each other. And they're going to be repelling in lots of different directions. But if you add up all the vectors of all the repulsions, you would end up with a normal vector of the repulsion. So what we've got is the reaction force is actually an electrostatic repulsive force. So now we've got all those forces there. Let's have a look at some triangles to represent them. We can look at the component of the weight force perpendicular and the component of the weight force parallel to the incline, and see that those two components add together to give the weight force. We can also look at the other three forces and see that they will describe a triangle where they all add together. Now you'll notice that I've drawn those two triangles above each other. They look really similar, but there is a difference. The one at the bottom, the red and green vectors are the perpendicular components of the weight force, and you notice that the green one is oriented down toward the bottom of the screen and the red one is also going toward the bottom of the screen. They will add together to give you the resultant weight force. At the top of the screen though, these three vectors are all drawn head to tail. And when they're drawn head to tail like that, that's representing that there is no net force acting on the object. It is in equilibrium. Now when we look down at the bottom triangle again, if I changed the weight force, which is mg, if I just change it to g and I've divided each side by m, we get this relationship between all of the acceleration vectors. So the red component the red vector component would give you the acceleration due to gravity down the incline, parallel down the incline. And in the top one, because we're looking at forces, the red component up and parallel to the incline indicates the force that's opposing that acceleration down the incline, and that's most likely going to be friction. So let's have a look at some example calculations that we can do on this type of a situation. These were two questions that have been sent to me, and I thought we'd look at them in a little bit of detail. So first of all, let's have a look at this one about a roller skater rolling down an incline at 25 degrees to the horizontal, not significantly affected by frictional forces, and we've got to determine the skater's acceleration. So here's a diagram of this person rolling down the incline at 25 degrees. They have a weight force down, which is mg, and that can be split into two components. There's the component parallel to the incline and the component which is perpendicular to the incline. Now I've just put in a few right angles there to show directions and orientations. I've got the 25 degree at the incline. We've got a right triangle which is here, and from that we can work out that this angle down the bottom is 65 degrees, and then from that we can draw a triangle of these forces where we've got the 25 degree, 65 degree and the right angle there. The perpendicular components are drawn that way, and we can determine what each of those components are, and we see that the one which is going down the incline and parallel to the incline is g sine 25. So what we've now worked out is the acceleration experienced by the skater down and parallel to the incline is g sine 25, which is 4.14 meters per second. Let's look at the second example, which is this young girl going down a water slide. Now it says that she's reached a constant speed of 35 kilometers per hour while she's sliding down the incline at an angle of 30 degrees to the horizontal, and it asks how long does she take to descend a vertical height of 12 meters once she reaches this constant speed. So let's do a few conversions. First of all, the kilometers per hour will convert to meters per second, and it approximates 9.72 meters per second. Then we draw a vector with the orientation of 30 degrees, and we can see that there's a vertical component of her velocity and also a horizontal component of her velocity. And when we're working out what the values of those are going to be, we can see that the vertical component is 4.86 meters per second. That is a constant vertical velocity. Why would it be a constant vertical velocity? Because we know that when objects fall under gravity, they accelerate. So why would this girl be travelling at a constant vertical velocity? The reason is that the water in this slide here is providing an upward force which opposes the force down the incline due to her acceleration due to gravity. So she's reached a constant velocity. She's no longer accelerating, and that's why she has a constant velocity there now. So now we can just plug that into the equation, average velocity is displacement on time, and determine that it took her 2.5 seconds to go down the incline. Okay, so they're the types of things that we can do. Drawing these vector diagrams are really important in your study of physics, and you've got to be quite familiar with them. And there's a few concepts you need to make sure you understand as well. So let's just check your understanding. Got a few questions here. First one, they're all true-false questions. The first one is the direction of the normal force the inclined plane exerts on an object, is that opposite in direction to that of mg? Well, no, it's not, because as I've said a number of times, normal force means perpendicular. So the normal force is perpendicular to the incline, whereas the weight force acts straight down toward the centre of the Earth. The next one is another true-false. The weight of a crate is 200 newtons. So will its weight on an inclined plane be smaller than 200 newtons? No, its weight is the force by which it is attracted to the Earth, and it's always going to be 200 newtons on Earth. And the next one, if this 200 newton crate is on an inclined plane, would the normal force exerted on it when it's placed on this inclined plane, will it be smaller than 200 newtons? It's true. It has to be smaller than 200 newtons. Always the normal force is the weight force times cos of theta, when theta is the angle of the incline. Because this cosine function will decrease as the angle increases, the normal force also decreases. So if it was a perpendicular incline, no, that's not going to work. Doesn't matter. Okay. What is the acceleration of an object sliding down a frictionless inclined plane? It will be equivalent to g sine theta. Okay, that's enough for now. Look, next video that I'm going to make is going to look at an investigation you can perform with your smartphone on an inclined plane, whereby you can use a number of little apps to look at the angle and the acceleration of your phone as it slides down the incline. And from that you can determine the frictional force between your phone and the inclined plane. So until next time, I'll see you then. Bye.